Let's read the situation. So again, we're solving problems, but we're going to formalize this a little bit. So you want to listen carefully. There's a couple of details that you really need to pick up on. So anybody who's not listening right now, like playing on your phone, probably want to put it away. So a ball is thrown, and the path of the ball is modeled by this equation. In the previous activity, I gave you the starting height or thereabouts and the maximum height and you know how far it travels to or whatever. And you were kind of building the equation. We didn't formally look at the equation, but that's basically what we were doing. We were making the equation. Now you've got the equation, and we're going to use it to solve a problem. Again, remember on Monday we talked about how math models real-world situations. So imagine now, again, it might be hard to imagine a situation where you care about a ball being thrown and when it hits the ground. Like, I get that, right? But it could be from a video game or something along those lines. And so what you do is you have this equation, and now you can use the equation to determine the different properties of where that ball is going to be at different times. That's the idea, right? And you couldn't do that precisely without mathematics. So a ball is thrown, the path of the ball is shown with that equation, where this is a bit of a technical thing. Don't get too caught up on it. H, okay, is the height in feet. It's good to look at the units. And D is the distance in feet. Okay, and so then I've taken that equation and graphed it with graphing technology, and there's the graph of it. I just cut the graph and put it in the lesson, right? So there it is. From what height was the ball thrown? Can anybody look at that graph and answer that question? Fine. It was thrown from 5? Thrown from 4. So there's where it's thrown. So from 4 and 4 what? 4 feet. What is that point on the graph? On Monday, we talked about the important properties of a parabola. What is that point, Sadie? Very nice, the y-intercept. So see, on Monday, we talked about how it was the y-intercept, and we talked about how it was a point, 0, 4. But now what we're really doing is we're using that understanding to solve a problem. So we're not labeling the point now. We're answering the question. From what height was the ball thrown? From 4 feet. Okay, good. What is the maximum height of the ball? Somebody else, what do you think? Josh, was that you? 5. Very good. So 5 feet. So there's the max height. What do we call that point? The vertex. Good. So the maximum height was 5 feet. And finally, our last question is, how far does the ball travel before it hits the ground? Somebody else? Tara, what do you think? Nice. Just over, I like that. About 3 feet. We don't know exactly. It's over 3 feet, but it's not 3.5. So I would estimate, and I don't know, I'm going to say about 3.3 feet. That's good enough for us. It doesn't have to be perfect, but that's the idea of what we're going for. Okay? So again, now we've got the equation. We can use it to actually get real data about this thing. If I was designing software that was supposed to fire rockets at my enemy, now I know where the rocket is going to land. So I hopefully aim it in the right spot. Right? And of course, it's a bit more complicated in real life even than that, but that's the idea. Okay, so this is the part that you want to write down. The y-intercept is where the object starts. This is why we talked about these important properties on Monday. Because it turns out they're usually the things to the questions we're trying to ask. They're usually the answers to the questions we're trying to ask. They're the interesting details about the situation that we're modeling, right? The real life situation. The y value of the vertex, so we saw that the maximum height occurs at the vertex, but it's just the y value. We don't care about x. So again, we don't answer it as a point, we answer it with words. So the y value of the vertex is the max, or it could be the min, but for us, everything we're doing, it's going to be the max. Height of the object. Quadratics and parabolas can model lots of other things other than just when you throw something in the air. There's lots and lots of other things in the world that you can model with, and some of them open upwards. Some of them go the other direction, so they do other things as well. And the X-Intercept is where the object hits the ground. And you'll notice some of the questions it's time, and for some it's distance. And that's an important distinction. In fact, there's two questions where it's like the same situation, but in one case you're talking about distance, in one case you're talking about time. And if you can reflect on that, it's really interesting to see how the equation changes and the parabola changes, even though it's the same like ball or whatever it is being thrown, because it's a model, right? So we use it when it's useful to us. Does that make sense? So here's what you're going to do for all the questions. You're given a question, and you have to answer those similar kinds of things, like where did it start, where did it hit the ground, and you're given the equation. You're going to use technology to graph it. That's all posted to the classroom. And you're also supposed to sketch it. So I'm going to show you what the sketch looks like. Okay, so the sketch would look like this. Oh, I've got an example right here. So let's do that same one that we did before. So when you open this on your Chromebook, it's going to look like this. I'm going to type it in. So that one was negative bracket. And instead of D, we have to use X always. So that's one of the things you really need to know. Don't use D or T. You have to use X. X minus 1 bracket. To do a squared, I've written it up on the board. It's shift 6. So that's like to the exponent 2. And then the equation was plus 5. And notice I don't put in the H equals. I just type in the rest of it. I hit enter. And there's that graph. That's basically the same graph we were just looking at. There's where it starts. There's the max height. There's where it hits the ground. Does that make sense? So then I'm going to, but the real life version of that would look like this, right? It starts where it starts and it ends when it hits the ground. It doesn't continue to go below the ground. But the mathematical version does. And that's why math is useful, but we need to be able to interpret the answers and think about what it means. It doesn't always match real life forever, right? So that would be like the real version. So when you graph yours, I would say probably you want to graph the real version. Okay, so we're going to start somewhere here, and my parabola kind of looked like that. And I'm going to just draw these points, and I'm going to label them. This was 4 feet. This was 5 feet. And this was about 3.3 feet. And I just label them like that. This is height H. This was D distance. Doesn't have to be accurate. There's no scale. Okay? I don't even use a ruler, but I'm labeling the important points and trying to make the shape look more or less like what it looked like on the computer. Does that make sense? Any questions?